In this video, we will take a look at the design of a counter using the finite state machine approach. We will take a look at the state diagram, the state table, and then the state assigned table. And we will look at the implementation of a simple counter using D flip-flops or JK flip-flops. Counters and counter-like circuits can be regarded as finite state machines, and they can be designed using state diagrams, state tables, and state assigned tables. Okay, a counter basically needs memory, because if we want to count up, for example, we need to know what the current count is so that we can then add 1 to it in order to count up. And so it has all the features of a finite state machine. It has memory, and then there is some combinational logic that computes what the next state is, like, for example, adding 1 to the current state. And there is also some logic that produces an output, which is the actual value of the count. So we will look here at the simple example of a 2-bit up counter, which is counting 0, 0, 0, 1, 1, 0, 1, 1, and then goes back to 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, etc. And we will look at how to implement such a counter using either D flip-flops or JK flip-flops. We assume that there is a binary input variable W, which is used to either stop the counter and keep the current count if W is equal to 0, or to increment the count if W is equal to 1, and we increment it by 1, and all of those things happen at the positive clock edge. So we are looking here at the synchronous counter. The state diagram of a 2-bit counter looks like this. We have 4 states, state A, state B, C, and D. In state A, we assume that the count is 0. In state B, it is 1. In state C, it is 2. And in state D, it is 3. And then we show here the transitions depending on what the value of W is. If W is 0, then we have the counter stopped at its current count. And so we just have a self loop around each of those states here. And if W is equal to 1, then we go from A to B, or from B to C, and from C to D, and then from D back to A again, which corresponds to incrementing the counter by 1. So the state table for this 2-bit counter is fairly simple. We have the present state, A, B, C, or D. If W is 0, then we stay in that state, so A goes to A, B goes to B, C goes to C, and D goes to D. If W is equal to 1, then we increment the count, so A goes to B, B goes to C, C goes to D, and D goes back to A. And the output, C, we just simply make 0, 1, 2, or 3, depending on whether we are in state A, B, C, or D. Now we look at the state assigned table for this 2-bit counter, and the simple way to assign bits to the states is to just simply take the binary representation of the count. So when we are in state A, which corresponds to count 0, we label this as 0, 0. If we are in state B, which corresponds to 1, we label it as 0, 1. State C, corresponding to 2, is 1, 0. And state D, corresponding to 3, is 1, 1. And then we can just replace the A, B, C, and D from the state table with the newly assigned binary values here, and we go from 0, 0 to 0, 0, 0, 1 to 0, 1, 1, 0 to 1, 0, 1, 1 to 1, 1, when W is equal to 0. And we go from 0, 0 to 0, 1, from 0, 1 to 0, 2, from 0, 1 to 1, 0, from 1, 0 to 1, 1, and from 1, 1 back to 0, 0. And the output bits are shown here. Those are the same thing as the present state. Now the next step will be to take this state assigned table and convert it into equations that we can apply to flip-flops, either D flip-flops or JK flip-flops in this example. So here we prepare for the implementation using D flip-flops. When we have D flip-flops, the flip-flop whose current state is the little yi has an input di, and that input di corresponds to the next state, capital yi. So capital yi in the state assigned table is the same thing as di for the D flip-flop. So now we're using Carnot maps for D1 and D0. And for example, for Y1, which now becomes D1, we're going to have a 1 when Y1, Y0 is 1, 0, or 1, 1. So in the Carnot map for 1, 0, 0 and 1, 1, 0, we're going to have a 1. So that's 1, 0, 0, that's this one here, and 1, 1, 0, that's the one here. So that's the case when W is equal to 0. When W is equal to 1, then and we need to correct that here. That should really say W1. So when W is equal to 1, then for D1, we're going to produce a 1 when we have 0, 1, and W1. So that means 0, 1, 1 in the Carnot map, or 1, 0, 1. So those are the two cases where we have a 1 there. So 0, 1, 1, 1, 0, 1. So here is 0, 1, 1, and here is 1, 0, 1. So that gives us the Carnot map for D1, and we group the bits together here. So those two are together. So that will make the Y1 W0. So that's this first one here. Then those two bits we group together. So that will be Y1 Y0. And then we have this bit here, which is all by its own. So that is Y10 ended with Y0, Y10 ended with Y0, and then ended with W. So that's the part back here. Then we do the same thing for D0. So D0 is going to be 1 for 0, 1, 0, and 1, 1, 0. So 0, 1, 0, that's here, and 1, 1, 0 is here. And it's also going to be 1 when W is equal to 1, when we have 0, 0, 1 in the Carnot map, or 1, 0, 1. So 0, 0, 1, that's here. 1, 0, 1 is back here. And if we group the bits here, we take those two together. So that will give us a Y0 ended with W0. So that's the first term here. And then we keep those two together. And so we have Y0 ended with W. So that's this term here. And we can take a look at the cost of this interface logic that we do here, that combinational logic. So we use, for D1, we use 1, 2, 3, 4 gates, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 inputs. And so that makes actually 14, not 11 here. Okay, so we have to correct this, make it a 14, and then for the D0, we have 1, 2, 3 gates, and then 1, 2, 3, 4, 5, 6 inputs. So 3 and 6, so we have to make a correction here too. That will give us a 9. And altogether we get now 23 for the total. Now the next question we can ask is whether we can extend this to more bits. We note that for D0 we can write this as being W XORed with Y0 or Y0. And for D1, it's a little bit more complicated, but we can group things in such a way that we take the W naught plus the Y0 naught, so ORed together, and then the whole thing ended with Y1, and then this ORed with W ended with Y0 and Y1 naught. And if we use De Morgan's theorem, we realize that W naught plus Y0 naught is the same thing as W ended with Y0 and then a naught over the whole thing. So that's what we have here. That gets ended with Y1 and then ORed with W ended with Y0 and that ended with Y1. So that is the same thing as W ended with Y0 and then this XORed with Y1. And so this suggests that we can extend that to D2, which is W ended with Y0 and Y1, and then XORed with Y2. And then the next logical one is D3, W ended with Y0, Y1, Y2, and then XORed with Y3, and so forth. And it does turn out that this is indeed the correct extension for more bits if you want to have a 3-bit or a 4-bit counter, for example. Now let's look at an implementation using JK flip-flops. In this case, we need to determine the values of J1, K1 for the higher order or the most significant bit flip-flop, and for J0, K0 for the least significant bit flip-flop. And we have to do this from the state assigned table. For JK flip-flop, if we want to go from a 0 at the input, from a 0 at the current state to a 0 for the next state, then we have to choose J to be 0 and K can be a don't care. Because if both J and K are 0, that means that the JK flip-flop stays in the same state, and so 0 will indeed go into 0. If K is equal to 1, then we have 0, 1 for JK, and that means that we reset the flip-flop, and so it also goes into the next state 0. If we want to go from a current state of 0 to a state of 1, then we have to set the flip-flop, and we can obtain this by making J equal to 1 and D equal to 0, but we can also just simply flip the 0 or toggle the 0 and make it into a 1, and in that case we would make J1 and D and K equals 1, and so the K is a don't care, only the J has to be 1 for sure. Then if you do the reverse, go from 1 to 0, we can do this again by toggling, so that would be J1, K1, or we can do it by setting J to 0 and K equal to 1, so J becomes a don't care here. And if you want to go from 1 to 1, from a current state of 1 to a next state of 1, then we can do so either by using JK both 0, or we can do this by setting J to 1 and K to 0, because that will set the flip-flop. So this leads to an excitation table for the 2-bit counter if we implemented the JK flip-flops. So we have the current state over here labeled with y1, little y1, little y0, and then the next state capital Y1, Y0, and W is 0, and the next state capital Y1, Y0, and W is equal to 1. And as we indicated in the table above, if we want to go from a 0 in the current state to a 0 in the next state, then J and K have to be set to 0 and D. And the same thing for that second bit here. If you want to go from the current state to the next state when W is equal to 1, then the first bit has to stay at 0, so that's a 0D for JK. And then the second one has to go from 0 to 1, so that is a 1D for the JK of that second flip-flop of the least significant bit. So this here would be the most significant bit, and this one would be the least significant bit. And then we do the same thing here for B. For the first bit, when W is 0, we stay at 0, so we use 0D. For J and K, for the other bit, we go from 1 to 1, and so we use D0 for J and K. Then if we have W equals 1, then we go from 0, 1 to 1, 0. So both bits have to change. 1 from 0 to 1, so we put in a 1D. The other one changes from 1 to 0, and so we put in a D1. And in this way, we continue through the rest of those columns here and fill it out as shown here. Now, because each of the two flip-flops has two inputs, a J and a K, we're going to get 4 Carnot maps for the whole thing to figure out what the equations for J1, K1, J0, and K0 should be. But it turns out we have now more flexibility because of the don't cares that we have in here. So the D in here stands for don't care. And so if we look, for example, at J1, then in the Carnot map, in the location 1, 0, 0 and 1, 1, 0, we have these. So 1, 0, 0 and 1, 1, 0, that's those two locations here. We have these in those. And then we have also for the J1 in the column where W is equal to 1, we have for 0, 1, 1, we have a 1 in the Carnot map, so that's down here. And then we have these for 1, 0, 1 and triple 1. So 1, 0, 1 is here, and triple 1 is here. So that fills in that first Carnot map. Then for the K1, we get a D for 000 and 010. So here's 000, 010. Then we get these also for 001 and 011. So 001 and 011. And we get the 1 here in the Carnot map location, which is 111. So that would be down here where we get the 1. And we similarly fill in the table for J0 and K0 with the Ds and the 1s. And then when we now get the expressions for J1 and K1, the SOP forms basically, what we find is that we combine those two here. We need to have the 1. Just keeping a single 1 would give us a larger expression, so we combine it with the D that's next to it, but there is no point combining it with anything else. And so that gives us Y0 ended with W. So that's this expression here. And we find for the K1, we're actually getting the same expression. Then for the J0, we have the whole bottom row that can be encircled. So that gives us W. And it turns out that for K, we get again the same row here, combining the don't cares. And so J0 is equal to K0, J1 is equal to K1. And it turns out that in this case, the cost is much smaller than what we have seen for the D flip-flops. So we have a cost of 3 for this AND gate here with 2 inputs, and we have a cost of 1 for just the W, just because that's an input into the flip-flop that requires some space on an FPGA, so we count that input as a cost of 1, and so the total cost is equal to 4 compared to the 23 that we found for the D flip-flops. Okay, and we can ask the question again whether it's possible to extend this to more bits. And we find that the logical extension here looks like we should set J2 equal to K2 equal to W ended with Y0 and Y1. So we basically add the next current state variable and AND it together with what we have for the J1, K1, and then we do the same thing for J3, K3. So we AND that J2, K2 expression together with Y2, and we can continue doing this, and it turns out that this does indeed give the right solution for a 3-bit counter or a 4-bit counter that counts up in increments of 1.